Hello everybody, welcome back to our channel. In this episode we're going to be solving a Physics 7B fluid transport practice problem. As usual, if you're finding this content helpful, please make sure to leave a like and subscribe. It really helps our channel. So this is a problem that we're going to be solving today. Make sure to pause the video in order to copy the instructions. I'm just going to read part A. So we have a segment of a pipe system in which water flows in a steady state to the right. The pipe system has a pump and three equally spaced standpipes as shown in the picture. The areas 1 and 3 are equal, and then area 2 is greater than 1 and 3. The first question is, assume resistance is negligible, rank the water levels in the three standpipes, explain your reasoning. So as you can see, I have everything written down here. So I have the picture, water is flowing from left to right, and R is equal to 0, and I just need to rank the water levels. So let's just go ahead and get started with this problem. So the first thing that we have to, figure out is how are we going to compare the water columns, because we can't use Bernoulli between water columns because these are different fluid systems. But we do know from the L and from working out several problems that the level on the water column is directly proportional to the pressure over here, because whatever level we have is going to be directly proportional to the pressure over here, because if you start at the top and then go towards the bottom, then you have delta P is equal to rho G change in Y. So basically what we are going to be comparing is the pressures over here at the bottom, just going horizontally through the pipe, and then the greater the pressure, the higher the water column. So let's just go ahead and just try to compare some points and get this, started. So we could really start with whatever 2 points we want. So I'm just gonna go ahead and start by comparing points 1 and 2. So I'm gonna use my Bernoulli equation from 1 to 2. So delta P from 1 to 2. And now, do I have a change in height? No, I don't. Do I have a change in area? Yes. So 1/2 rho delta V squared. Resistance is negligible, so there is no resistance term. But if I'm going from 1 to 2, there is a pump, so E pump divided by volume. Now, the exercise here, what I have to do now is figure out whether these guys are positive or negative, and after that should be able, we should be able to figure out if delta P is positive or negative. Now, this term, the energy density that the pump is adding is positive. Pumps never take energy away from the system. Pumps can only add energy to the system. So this term is always going to be positive. Now, this term over here, this one can either be positive or negative by definition. So we need to figure it out by looking at what we have. Now, in this particular case, when I go from point 1 to point 2, my area goes from small to big. Now we know, because of the continuity equation, I1 has to be equal to I2, so A1, B1 has to be equal to A2, B2. We know that if you increase the area, then your velocity decreases in order to have continuity in your system. If the velocity decreases, that means that you have a decrease in your kinetic energy term. Therefore, this guy has to be a minus. And I think that we have enough information to figure out what delta P is, because this number over here, which is the one that we're interested, plus a negative number, needs to end up a positive number. Now, if this delta P were a negative, negative plus negative that just wouldn't be, that there's just no way that you can make a positive out of two negatives. So this means that this guy is a plus. Now if this guy is a plus, delta P1 to 2 is equal to a positive number, then delta P by definition is final minus initial, so this is 1 and this is plus. If 2 minus 1 is equal to a positive number, that means that the pressure at 2 is higher than the pressure at 1. So the water column at 2 has to be greater than the water column at 1. So we know that. Now this isn't really giving us any information from 3, so I'm just gonna go ahead and do Bernoulli from 2 to 3. So let's just go ahead and do that. So Bernoulli equation from 2 to 3. Now this is going to be delta P start at 2, finish at 3. Now from 2 to 3, there isn't a change in height, but there is a change in area. So 1/2 rho del B squared. And we don't have a resistance, so there is no resistance term. And also, we don't have a pump when we go from 2 to 3, so this equation is actually going to be equal to 0. Now, if we can figure out the term, whether this is plus or minus, then this one would have to be the opposite. So let's just go ahead and look at it. When we go from 2 to 3, then our continuity equation will basically just be 2v2 is equal to a3v3. Going from 2 to 3, your area decreases. This means that your velocity increases. So you went from slow to fast. This means that your kinetic energy term increased because your velocity increased. And because this number plus this number have to equal to 0, meaning they have to literally cancel each other out, this term needs to be a negative number, because otherwise plus and plus they are never going to cancel out to 0. This has to be negative. So delta P from 2 to 3 is a negative number. So P3 minus P2 is a negative number. This means that this guy is greater because the result is a negative number. And from this information, we know that the highest water column has to be the second one, because 2 is greater than both 1 and 3. Now at this point, it might seem like, we have enough to give a final answer, but actually we don't, because even though we know that 2 is the highest pressure, we don't really know how 1 and 3 are related to each other. 3 could be higher than 1, 1 could be higher than 3, or they might be at the exact same height. So we actually need to do this one more time in order to figure it out. So let's just go ahead and do that real fast. So Bernoulli equation from 1 to 3, because we want to compare 1 and 3. So if I go from 1 to 3, this is delta P, start at 1, finish at 3. I don't have a change in area because the areas are the same. I don't have a change in height. I don't have a resistance. The only thing that I have between 1 and 3 is actually this pump. So this is just going to be equal to the energy density of the pump, like this. Now, like I said, this term right here, this is a pump. A pump doesn't really take energy away out of the system. It can only give energy. So this number is going to be positive always. And because this number on the right side of the equation is a positive, that means that this number on the left side of the equation has to be a positive, right? I mean, plus has to be equal to plus. So delta P from 1 to 3 is equal to a positive number, and it's also equal to 3 minus 1, which means that 3 is higher than 1. And now we can actually, this is the final answer. So final answer for this first part of the quiz will be that pressure 2 is the highest, and then pressure 3 is the second highest, and then the lowest pressure will be pressure 1, which means that if I want to make this a drawing, then I need 2 to be the highest, so let's just make it very high like this. And then 3 needs to be the second highest, and then I just need to be careful that 1 is the lowest. So there we go. So this basically finishes up the first part of the problem. Now, if you look at the instructions say explain your reasoning. So students were very much invited to, you know, maybe try to explain this with words. Now, obviously, even if you decide to explain something with words, we do need, you know, the explanation needed to be pretty much what I'm expressing here in equations, which is that, you know, oh, 3 has to be greater because the energy adds, the pump adds energy density, or, you know, just something. You were allowed to use your words, and then, you know, that would be evaluated. But this would be, you know, pretty much the most straightforward, at least in my opinion, way to do it, because even though, yes, it's a little tedious, you know, there really is no better way to explain your answers in physics but to give like actual math. Besides, this is a tutorial, so I just thought, you know, let's just do it the, you know, the best way possible. So now let's just go ahead and read the second part of this problem, because this actually has 2 parts. So the second part says, the pipe system described above gets clogged, so resistance becomes significant. So now we actually have some resistance, you know, over here in the horizontal pipe, and it is uniform throughout the pipe. Assume the speed of the fluid in region 1 is 3 meters per second, that area 1 is 1 meter squared, area 2 is 2 meters squared. The water level increase from standpipe 1 to 2 is 0.2 meters. So now we know that, okay, so let's see. So let's just say that, you know, we have this water level and we have this water level over here. And this, you know, this is 0.2 meters of a difference going from here to here. And then decrease from 2 to 3 is 0.6. So 3 is now the lowest. And this distance from here to here is 0.6 meters, which means that the total distance from here to here would be 0.4 meters, which I don't know if that's going to be useful, but we'll see. Anyways, the instructions are: find the resistance of the horizontal pipe between regions 1 and 3, which is this R, and find the energy of the pump per unit volume. Show your work. Okay, so this is where things get a little tricky, because now we have resistance on our pipe, and obviously that is going to change, you know, pretty much everything. For starters, with no resistance, the height of the pipes used to be that 3 was higher than 1, and now that there is resistance, this affects the equilibrium state here in our fluid system. So we really need to sort of like take a step back from what we've done and, you know, yeah, pretty much start over. Now, the first thing that we could try to solve this problem would maybe be using our Bernoulli equation again. You know, maybe from 1 to 2 or from 1 to 3, and just try to come up with something in which we can solve for R, or E pump divided by volume. The first thing that I'm gonna do to just get that out of the way, because I'm gonna need it, is find the velocity at point 2. Now the velocity at point 3 is just the velocity at point 1, because these areas are the same, and because these areas are the same, then this is just 3 meters per second, so that's easy to figure out. Now, in order to figure out what the velocity over here is, I need to use continuity. So the flow crossing here has to be the same as the flow crossing here. So this is flow 2, so A1 B1 is equal to A2 B2. So velocity at point 2 is equal to area 1, velocity 1 divided by area 2. So area 1 is 1, 3 divided by 2, so B2 is 3/2. Okay, so this is going to be useful information. And another thing that's going to be useful, because R always comes with an I on the Bernoulli equation, is just knowing what the flow is. The flow is just an area times a velocity, so flow is just area 1, velocity 1, so it's going to be equal to 3 meters cubed seconds. There we go. So this is also going to be useful information. All right, so the tricky thing here is that, you know, there are a lot of ways in which you can solve this problem, or well, I should say there are a lot of ways in which you can start solving this problem. Some of them will end up being very long procedures. Some of them might be more clever procedures. So regardless, you know, if you did this a little bit different than I, so long as your answers are, you know, so long as you can explain your answer and it's logically okay, then that's totally fine. I'm just gonna show you the way in which I would solve the problem, and I'm just gonna, you know, sort of like talk about how I would solve the problem. So I know that, you know, a first sort of like intuition would be that if R and E are both over here on the horizontal pipe, then what I should be doing is applying my Bernoulli equation on the horizontal pipe. And that is something that, you know, maybe 99% of students did, so fine, let's just go ahead and do that to see what's gonna happen. So let's just start by doing, say, let's compare points 1 and 2 and then 2 to 3. Let's just go with that. So Bernoulli from 1 to 2. Now this will be delta P, start at 1 end at 2. Now again, I don't have a change in height. I do have a change in area, so this is 1/2 rho delta V squared. I do have a pump between 1 and 2, which I would like to solve for. Ideally, I need to find this actually. And now I actually have a resistance, so I need to do negative I R. And it is important to notice that this R is just resistance from 1 to 2. So this R is not really what I'm looking for. It would be just half of that. Now, this immediately spells a little bit of trouble for us, because this term over here I can figure out. I have both of the velocities. Rho is just a number, it's just 1,000. So this is a number that I can put on a calculator right now. However, I don't know this term. I don't know this term. And also I have no idea about this term as well, because I have no, I don't know what the pressures are. So the next thing would be, well, maybe what happens if I use my Bernoulli equation, say, from 2 to 3 then. So let's just take the pump out of the equation. Well, Bernoulli equation from 2 to 3 would be delta P, start at 2, go to 3. I don't have a change in height if I go from 2 to 3. I do have a change in area. I don't have a pump, but I still have a resistance. So this would be resistance 2 to 3. Now from here, I could easily, so this is a number that again I can calculate because I do have the velocity at 3 and the velocity at 2. So I could easily just put this part on a calculator. I already have, so this can go on a calculator, but I don't really have this R over here. It wasn't given to me. And also, I don't know what this delta P is. So yes, this looks a little bit more promising than this, because at least this is 2 things that we don't know versus 3 things that we don't know. But you know, we still don't really have any kind of way to solve this problem by just using the Bernoulli equation over here. Now, just sort of like taking a pause over here, you might think, well, luckily for us, we also have this information, right? We also have this height difference over here, and we have this height difference over here. And this is where, you know, things get a little bit complicated, because this is a height difference from this water column to this water column. It's not a height difference from the top of the column to the bottom of the column. Meaning, I can't just use my Bernoulli equation and call it delta P, because I can't use my Bernoulli equation from here to here, because I'm basically crossing several fluid systems, and that would be theoretically incorrect to try to use Bernoulli from here to here. You can't cross water columns, that is just not okay. But what we can do is set up a reference and then just use our Bernoulli equation separately 3 times in order to get, you know, some sort of relationship, and see if we can maybe come up with a useful way to use this guy and this guy over here. So the first thing that I'm gonna do is I'm gonna call this height over here, over here, and over here a reference height. So I'm gonna call it Y ref. It is a reference point because all of the water columns end over here. So I think it would be useful to have a reference point. Now what I'm gonna do is I'm gonna use my Bernoulli equation, column 1, going down. This means start over here and then go down like this. Now if I do this, this is delta P from top to bottom. Right, so this is delta P from top to bottom, and now I don't have a change in area because this is a water column. Water is not moving. There is no flow, so there is no IR term, and there is also no pump. So the only term that survives would be rho g change in height, and this has to be equal to 0. Now if I start on the water column 1 and I'm going down, this delta P is basically all of these are open to the atmosphere. And I decided to go down, which is final minus initial. So final would be P at point 1, the pressure at 1, minus atmospheric pressure. And then this change in height would be final minus initial. So this would be the reference. A reference height minus, you know, the top of the first water column. I'm going to call this Y1, I'm going to call this Y2, and I'm going to call this Y3. Like this, and this has to be equal to 0. So let me just rearrange this a little bit. So pressure 1 minus atmospheric pressure, and then I'm just going to split this up. You'll see why in a second. And this is the equation that I get. Now, these 2 water columns, even though the water difference is the same, if I apply the Bernoulli equation to these 2 water columns, they would basically look exactly the same, because if I go from here and I go down like this, you know, I don't have a pump, I don't have a change in area, I don't have a flow, so and so. So if I do the exact same procedure, except I now do it for columns 2 and columns and 3, then my other 2 equations would be, you know, instead of 1, it would just be 2 minus PATM plus rho g y reference point minus rho g y2 is equal to 0. That would be the equation if I go this way. Feel free to, you know, just start over here and then working your way to it. And for pressure 3, it would be pressure 3 minus atmospheric pressure plus rho g y ref minus rho g y3 in this case is equal to 0. And I feel like at this point you should sort of like see where I am going. At this point I have an equation that would give me pressure 1, an equation that would give me pressure 2, and an equation that would give me pressure 3. So the way in which I can grab these auxiliary equations that I created in order to put them down here, which is, you know, where I need them, I basically I'm gonna subtract them. So I'm just gonna subtract both of the equations. Say for example, if I want delta P from 2 to 3, then what I should be doing is and I want it so that I would be able to put it over here, because if I put something here, then I can solve for this. So if I want 2 to 3, then I need to do 3 minus 2, right? So I need to take this equation and then subtract this equation. So let me just do that. So if I take this minus this, then the equation would be pressure at 3 minus pressure at 2. These two are going to cancel out because I'm subtracting them. These two are going to cancel out because I am subtracting them. And then these two I am going to keep. So it's this one minus this one. So it's is equal to 0. So now as you can see, this guy over here is delta P final minus initial, so it's 2 to 3, which is exactly what we need. And this guy over here is you know, I can arrange it so that it looks like rho g y3 minus y2 is equal to 0 like this. So this is delta P 2 to 3 plus rho g, changing height from 3 to 2 is equal to 0. So delta P from 2 to 3 is equal to negative, because I'm sending it to the other side of the equation, 1000 because this is water, 10, and then delta y from 3 to 2, delta y from 3 to 2 is equal to 0.6 meters. It's actually an increase because you're going from low to high. You're going from 3 to 2. So this is positive 0.6 meters. So this is negative 6,000 pascals. And now this is a very useful number, because now we know that this guy over here is negative 6,000 pascals. This is 1/2 of 1,000. This velocity came from doing from 2 to 3, so it's 3 minus 2. That means 3 squared minus 3/2 squared. And then I have to divide by negative 3. And this is going to be equal to r from 2 to 3. So now I can actually put something on a calculator thanks to my auxiliary equations. So let me just go ahead and do that right now. Let's see. So negative negative 6,000 plus 1/2 times 1,000 times 3 squared minus 3/2 squared like this, and then divide by -3, 875. So R from 2 to 3 is equal to 875 joules seconds meters 6. But now we actually have to wait a second over here, because this 875 it is the total resistance from 2 to 3, and the problem was asking me what is the total resistance from 1 to 3, not from 2 to 3. So this is a little bit of a tricky thing, right? Because you went all this way and this isn't even the final answer. However, the problem is saying that all of these pipes are equidistant to each other, and it is also saying that resistance is uniform throughout the pipe. So if the resistance from this point to this point is 875, and this distance is equidistant to this distance, then the total resistance is just double that, because it's double the length. So final answer for the total resistance from 1 to 3 is 875 times 2. So multiply answer times 2, and this is 1750 joules seconds meters 6. Final answer. Alright, so now we basically have to do the same thing, figure out this delta P, and now that we can put something in here, then we should be able to solve for the pump. So let's just go ahead and do that. So going back to my auxiliary equations, now what I need is delta P from 1 to 2. So the two auxiliary equations that I'm going to be subtracting from each other is, if I want delta P from 1 to 2, then I need to be subtracting 2 minus 1. So I'm going to take this and subtract this. So this is equal to pressure at 2 minus pressure at 1. The atmospheric pressures are going to cancel each other because they are subtracting each other. These two reference points are going to cancel each other out. And these two are the terms that are going to stay here. Is equal to 0. Now this thing over here is the delta P that I want to figure out in order to put it over here. So this is delta P from 1 to 2. And obviously it is defined as 2 minus 1. And this term over here can be rearranged to be 1 minus 2, right? Is equal to 0. So delta P 1 to 2 is equal to negative rho g. If it's 1 minus 2, then this is delta y from 1 to 2. Oh, and that's it. So delta P from 1 to 2 is equal to negative 1000 times 10. And if you go, sorry about that, if you go from 1 to 2, then you are increasing your height. So your height is actually increasing. So let's see. Wait a second. Oh no, there we go. There we go. So this is where I made a mistake. So this is 1 minus 2, and because deltas are final minus initial, this is actually delta y from 2 to 1. There we go. Yeah, delta P1 to 2 has to do, is related to delta y2 to 1. Okay, so this delta y is actually start at 2 and go to 1. And as you can see, the height difference is 0.2 meters, but when you start at 2 and go to 1, you had a decrease in height. So this 0.2 has to be negative, like this. So delta P from 1 to 2 is equal to positive because the negatives make up a positive, and then 2000. There we go. 2000 pascals, so you just multiply all of this and then cancel the negatives. So this number is a 2000, like this. This number is 1/2 1000 delta b squared. If I go from 1 to 2, this is final minus initial, so 3/2 squared minus 3 squared. E pump is what I'm looking for. Minus I is equal to 3. And this is important. Which number am I going to use? Am I going to use this number or this number? Well, this number is from 2 to 3, so it's not okay. This number is from 1 to 3, so that is also not from 1 to 2. But we know that these pipes are equidistant and the resistance is uniform. So if the total resistance here is 875, then the total resistance here is also 875. So R from 1 to 2 is 875, so that they can add up to the total resistance, right? So I have to use 875 over here, like this. So E pump divided by volume is, so I just need to put this on a calculator. So this would be 2000 plus 1/2 1000 3/2 squared minus 3 squared close plus, because this goes to the other side of the equation, 875. There we go. So 1250 joules divided by meters cubed. Final answer. And this is our final answer, and this is our final answer, and now finally this problem is complete. Now obviously this quiz was a little bit on the longer side. It was a 30-minute quiz, not a 20-minute quiz. Now obviously time was still tight on this quiz. The amount of things that we have to do is not trivial, but you know, if you're thinking, how am I going to be able to do this in 20 minutes? Well, it was 30 minutes and, you know, also just practice. But yeah, we did use a bunch of auxiliary equations. Now obviously this makes a problem a little bit on the harder side. If you feel like there's just, you know, this was a little bit overwhelming, please remember that this is a problem that I marked as a challenging problem. So if this is a little bit too complicated at the moment, my recommendation is try going back a little bit to like maybe the yellow problems, or maybe, you know, just start at whatever difficulty level you're actually comfortable with and try to build up to this. There is actually nothing on this problem that you know, that you wouldn't see on DL or in lecture. It was just that, you know, it's sort of like it's a big procedure, and that's pretty much it. But when you think about it, every single thing that we didn't just come out of it, you know, out of the blue. So what I'm trying to say is, don't get discouraged by this problem. This is a 7B problem. This was a quiz, and I do not think at all that this quiz was too unfair or too hard or anything like that. That is not my opinion at all. I think it was fair, challenging, yes, but fair. And so don't feel overwhelmed by it. Just try to work it out step by step. You know, take your time with the problem. Try to do the steps by yourself, because that's really how it's going to make sense to you if you actually do the procedure and if you actually follow the lines yourself. And you know, other than that, it's just a matter of practice. So as usual, guys, if you found this helpful, please make sure to leave a like. We do read the comments and we do appreciate your feedback. So I'll see you guys in the next video.